Well, welcome to the McCarthy Observatory. Thank you for coming out on this less than perfect night. My name is Bill Cloutier. I've been a volunteer here for, let's see, at least 18 years. I guess I stopped counting at some point. But I'm glad you came, and please come back, and hopefully we'll have even better weather next month. Tonight, my topic is space travel and some of the health effects and what it does to the human body once we leave the Earth. We are creatures of gravity. The human body was built for getting around, very efficient machine. We have a skeleton that provides many different functions. It supports the soft tissue and the body's weight. It stores nutrients. It contains marrow for blood production. It protects our vital organs, the spinal column, the brain, the other vital organs that we depend upon. Our circulatory system is designed to pump against gravity. Gravity normally pulls the blood in the lower part of the body, and our heart is designed to circulate it back up towards the upper parts of the body. Our eyes, our ears, they work together to provide the brain some sense of our orientation. Are we lying down? Are we standing up? All in reference to the gravity field that we live under. And of course we have limbs that get us around, that if we didn't have gravity, we wouldn't necessarily need. So all in all, we're very comfortable here. We have a very stable star that provides warmth. We have a planet that has ample resources. We could use a few less mosquitoes, but other than that, we're pretty comfortable. As planets go. And as we look out into the galaxy and we constantly finding new planets, we haven't really found those planets that are as good for supporting life as we have here. So we're very lucky in that respect. But as humans, we are very curious. We're willing to take risks. We're willing to push the boundaries. The bottom of our oceans and the top of our mountains are littered with explorers that were willing to take that risk and venture out, defy the odds. There's always, especially the very young, their most common question is why. So it's not surprising that we'd be willing to look beyond where we're comfortable and venture into those places where we might not be so comfortable. But it comes at a price. Once you leave the Earth and enter microgravity or weightlessness, you have to adapt because, again, the human body wasn't designed for that. And we'll get into a little bit of details, but what we've seen so far in our explorations of near Earth and even the Moon is that over the long term, we start to experiencing bone loss. The fluids in our bodies start to shift because there's no gravity to pull them into their rightful place. We start losing some of our fine motor skills. Deprivation. We find that astronauts start missing the cool green hills of Earth, that sea breeze, that the environment is always the same. It never changes. Fortunately, if you're on the International Space Station, you get to look out at the window and look down at the Earth. But once you get into deep space, you're pretty much looking out into the void. So all those colors, all that companionship, it starts to wear on your psyche. But it's not impossible. In fact, we seem to revel in doing the impossible. I do remember that, many years ago, the New York Times published an editorial chastising Robert Goddard, who was the father of American rocketry. And they essentially told him he was wasting his time designing rockets because they would never work in space. And I think sometime around the time that Neil Armstrong stepped on the moon, the New York Times had to publish a retraction to that. So even though it may sound futuristic and science fiction and totally beyond belief, we as an intelligent race have been able to conquer many of those challenges and move forward. So as you can see, we'll go over some of these challenges, and of course the one at the bottom of the page is one of the real areas where we need to do a lot more work, because once we leave the Earth, we're traveling into a radiation-filled void. We also get conflicting information, as I mentioned. You know, the eyes and the ears work together to tell the brain which way is up. But once you get into a weightless environment, it's sometimes not so easy to tell. In fact, sometimes they have to have clues, like signs on the wall that can orientate the astronauts. In some cases, it doesn't matter. The nice thing about living in weightlessness is that you can use the ceiling and the walls for workspace just as well as you could use the floor. But the body does get confused, and sometimes it takes quite a while for it to adjust. There have been instances where astronauts during their sleep cycle have woken up and been surprised to see something floating in front of their face, not realizing it was their arm. The brain was not giving the signals that the arm was there. So it was a bit of a surprise to see these things floating around. I know one of the early Gemini astronauts reported seeing a glowing object in front of him. It turned out to be his watch. He just wasn't getting the signals to his brain that his arm was attached to his body and was actually in that location. So there are some challenges, and one of the big ones that we have come across and we've done a lot of work on is the skeleton and what happens to the bone. Now, on Earth, and as you're sitting here tonight, your bones are being constantly broken down and renewed. And as long as that process is in balance, meaning that the rebuilding rate is equal to the removal rate, then you're a healthy individual. What happens in microgravity, interestingly enough, is that we believe that the breakdown continues at its current or maybe even a slightly accelerated rate, but the rebuilding is slower. So the overall process is out of balance. And what happens is that the bones start getting weaker, 10 times faster than what might occur on Earth. And we saw that quite a bit in the Russian cosmonauts when they had a space station. They really didn't have any room to do a lot of physical exercise to put any stress on their bones. So when they came back to Earth, their bones were considerably less dense, and it took their bones a long time, longer than they were in space, to recover. Now we've done a lot of research on this. So if you've ever watched the NASA channel, you'll see that the astronauts spend a lot of time exercising. Resistance exercises. You're not actually lifting weights, but you've got machines that put a stress on your bones. So the bones are in a situation where they can rebuild at a somewhat comparable rate to what we have on Earth. Now we still don't know if the bones are as strong as they would be on Earth, or if they're growing in the same locations. For example, we found that the leg bones tend to do quite well in space with exercise. We find the rebuilding is comparable, but not necessarily the hip bones. So when you're talking about someone like Peggy Whitson, who you might know, she just set a record in April of the longest duration in space by a U.S. astronaut. Not consecutive, but she's been up there for several missions, and she's there right now. In fact, she just completed the 200th spacewalk for the International Space Station just a day or two ago. But they've noticed that while her bones have done very well in weightlessness, as long as she maintained a regimen of exercise, while her legs have gained a lot of bone, her hips not so much. So whether that affects her later in life, as far as hip fractures, we're not sure. We're not really sure yet of some of the mechanisms of why the bones deposit in some locations and not others. But again, there's certainly a lot of research in this area. There's medications that are being developed, and nutritional studies that have been worked up to provide the astronauts the best chance they have as far as maintaining a healthy body. This is Peggy again. You can see that she looks a little puffy in the picture on the right there as the fluids have shifted in the human body. What happens is that mostly from the legs, the fluids start working up into the chest area and up to towards the head. You get not only blood, but other fluids tend to have a different reaction in weightlessness. Now, on Earth, fluid collects in your bladder. It expands your bladder and sends a signal that it's time to leave this talk and head to the restroom. In space, the fluid tends to just accumulate around the walls of the bladder, and it's not until the bladder is completely full that you get any kind of sensation that you need to relieve yourself, which is another problem, because then an extremely full bladder tends to press on other parts of the body and inhibit some of that reaction. So it's a very different situation in zero gravity. And that includes the eye. Now, there is increased pressure in the skull in weightlessness, and that tends to push on the back of the eye. So you see that lower picture, the eye globe is not quite round. It also pinches the optic nerve, and it changes your whole vision. And sometimes, in most cases, when you come back to Earth, your vision returns to normal, but not always. They were so worried about this going back to the early 60s that when John Glenn made the first flight around the Earth, the doctors installed little tiny eye charts on his control panel in the Mercury capsule so they could monitor the changes in vision to make sure that he was capable of conducting the full mission and returning to Earth. They were very concerned that the changes in the eye would be so severe that he wouldn't be able to carry on. We found that it's not quite that bad, but it does have an effect on the astronauts, particularly for long duration flights. The other real challenge that I mentioned earlier is radiation. We are very fortunate to live on a planet that has a magnetic field and a dense atmosphere that shields us from most of the radiation that is present at higher altitudes and in low Earth orbit. As you can see, the higher you get in our atmosphere, the more radiation and dose you're exposed to. And of course, over a long period of time, it has health consequences. Now, there's two major sources of radiation from the sun. And of course, you're all exposed to that when you go to the beach, and you're exposed to the ultraviolet from the sun. But the sun also produces X-rays and gamma rays and high-energy protons, which is just the hydrogen atom being stripped of its electron. The other source, and potentially even more severe as far as consequences to the human body, is from the galaxy. And it comes from all kinds of high-energy events. When a star explodes, it radiates the area nearby with the whole spectrum of radiation. Mostly hydrogen and helium atoms that have been stripped of their electrons, so they now become charged particles. But 1% of the galactic cosmic rays are called heavy elements. Elements like iron and heavier. That the electrons have been stripped off the nucleus. So now you have a charged particle traveling at the speed of light. And these things are very disruptive to our biology. They just pass through the body, ripping our cellular DNA to shreds. Very difficult to shield against. In fact, shielding sometimes tends to make it worse, because the cosmic rays will interact with the shield and actually produce a secondary shower of radiation. So, again, these are challenges. They're not insurmountable, but they will have to be solved before we can spend any time away from Mother Earth. The interesting thing about those two sources of radiation is that when the sun is very active, its magnetic field intensifies and it deflects the radiation from the rest of the galaxy. What we're seeing right now is that our sun is going into a low period of activity, low part of its cycle. And as a result, in this chart, you can see that in the past 2 years, galactic radiation levels have increased quite a bit. So when it comes to space travel, it's all a matter of timing. You can either deal with the solar radiation, or you can deal with the galactic radiation. There's some thought that this next solar cycle, when the sun starts to ramp back up again, we don't expect a very strong cycle, but it might be strong enough to deflect cosmic radiation. It might be a good time for a mission to Mars, when most of that galactic radiation is being swept away by increased solar activity. So if you're going to Mars, or anywhere else in our solar system, you've got to learn how to live and work in weightlessness or microgravity. As we talked a little bit about, the human body is just not something that adapts quickly to new surroundings. So fortunately, we have a place to learn. And back in 1998, the Russians launched a module, and about 3 weeks later, the Space Shuttle Endeavour docked with that module and delivered a second component. And since then, and it's taken over 115 space flights, and as we talked about earlier, over 200 spacewalks to pull it all together, we have a laboratory in orbit around the Earth where we can work out all these challenges of living and working and going beyond low Earth orbit. And the U.S. segment has also been designated as a national lab. So if you follow work on the International Space Station, you'll see that there's quite a bit of medical research going on. We are fortunate that we have spacecraft like the SpaceX Dragon that can return samples to Earth so that researchers can deliver experiments and biological material to orbit and then return it back to Earth for analysis. So if you, it's a topic for, I would imagine, a whole new talk, but there've been some progress on some very serious medical conditions. I know I've seen experiments up there on Alzheimer's where they can do things in microgravity that weren't possible on Earth because the gravity tended to clump the proteins together, and in microgravity they could allow these proteins that are either a symptom or a cause of Alzheimer's to grow longer and not to get entangled with one another. So they could study the properties better in microgravity than they could on Earth. So there's some real interesting work being done up there, and again, that's a topic that we should address at some point, especially with some of the results that are coming out of the work being done up there. And one of the things that you probably saw in the news was the twin study, where we had two astronauts, one Russian, one US, that spent almost a year in orbit so that researchers could get a feel of what the effects of long-term weightlessness were on the human body. And fortunately, the US astronaut, Scott Kelly, had a twin brother who was also an astronaut. So they were able to study the genetic impact of having one twin in space and the other one as a control subject that they could poke and prod on Earth. So Scott has returned. The findings are just starting to come out in papers. And what I've seen so far is that individual results have been published. But now the researchers are all getting together and looking at the whole picture to see if there's interconnections between the changes in the human body. Very interesting study, and I think most of that will be starting to come out in published papers later this year. So now if we're going to leave Earth orbit, we've got some additional challenges. Okay, it's not it's quite as safe as the folks on the International Space Station. Of course, they're only 200 miles up, and they have space vehicles parked at the space station full time, so if there was a medical emergency, they could return to Earth within a day or less. Now, once you leave the Earth, you have fewer options. As if anyone saw the movie The Martian, you realize there are many challenges out there, both physiological and psychological. Your options decrease. As I mentioned, you just can't hop into a capsule parked at the space station and return to Earth. Communications become more difficult. Now, if we go to Mars, it depends upon the scenario, depends upon the spacecraft that are available to take us there. It depends upon where Mars is in its orbit. But, you know, one example is 9 months out, 3 months on Mars, 9 months back. So almost 2 years. off the Earth. And that's probably a fairly optimistic scenario. One thing the human body it takes a while to get used to is different gravity fields. So here you're leaving the one gravity field of Earth. You're going into a weightless environment potentially for 9 months. You're landing on Mars that has a gravity about 1/3 the Earth. After 3 months you're leaving that, going back into weightlessness for 9 months. And then you have to deal with the full gravity of Earth once you return. So there's challenges throughout that time period of keeping your body in sufficient condition so that you can live and work not only in space, but once you get to Mars. Are you going to be able to function in the Martian environment? And then once you come back, what's the likelihood that you'll be able to return to Earth? There's been a lot of studies on keeping people confined in small spaces. And it's no different than when you put even the most highly trained astronauts in a small capsule. Over a long duration, you're going to see that it's going to affect their mood, their morale, their interaction, their personal skills. The sleep cycles can be easily disrupted, so that that'll also make you potentially depressed and out of sorts. Fatigue, even though it may not be strenuous work, fatigue will take its toll, and you're going to potentially have misunderstandings and communication difficulties. Think about a spacecraft, how small it is. You've only got so much air, so much water. You essentially have a little confined world. And what they found out on the space station is that you tend to have company. Bacteria, microbes tend to start developing little own colonies to spend some time with you. Since you're in close confines, passing any kind of cold or virus becomes a lot easier. Your immune system starts to weaken. So you really have to be careful, because you're more susceptible in these small, closed environments. And that's just a petri dish of some microbes that were swabbed off the walls of the International Space Station. Getting back to space radiation. So the International Space Station orbits inside the radiation belts of the Earth. So it's provided protection by those radiation belts, that magnetic field of the Earth. Once you leave that, you're subjected to, again, those bombardment of not only the radiation from the sun, but also from the galaxy. As it mentions on the slide, radiation also has an effect on your food. It can decrease the nutritional value. It may decrease the effectiveness of medications that are being carried on board. So it's something that we're going to have to work on. Mars is a long ways away. I mean, at least at the observatory here, we don't usually talk about Mars until it's close by. Until it reaches opposition and it's fairly close, we can see it in the sky. But that only happens once every 26 months. That other 25 months, Mars is either moving away from us or we're moving away from it. So not only do we have distance, but we have the inability to travel long distances quickly. So if there was an emergency, there's no way of turning back. You would actually have to deal with it. So the astronauts on board of any spacecraft to Mars are going to have to be self-sufficient, able to take care of any crisis that comes up. There's going to be a communication delay with the Earth, so it's not like you can call them up and get an instant response. They're going to have to be able to take care of minor medical emergencies. So they're going to have to be jacks of all trades. So that's all the bad news. So what can we do about it? How can we mitigate some of the negatives? Well, the first thing is get to Mars quicker. Time will solve a lot of our problems. If you're worried about radiation, don't spend so much time in the radiation field. If you're worried about the amount of supplies you're taking with you, well, don't spend as much time getting there. So if you can shorten the trip by some means, you shorten or mitigate all the negative effects to a great degree. Improve the living conditions. Can we send larger or more comfortable spacecraft so that you're not cramped and you've got some place to go and get away from the rest of your crewmates sometimes? Can we generate artificial gravity? That would certainly solve some health aspects. Can we generate a magnetic field to deflect some of that radiation? Or maybe we can just sleep the whole trip. So these are, while some of these things sound like science fiction, these are actual areas where research is being done. The first one you probably are familiar with. There are several companies building larger rockets. We're working on more exotic means of propulsion, which could shorten the trip. We could deploy supplies. We could actually send robotic teams to the surface of Mars to prepare it for us, so we wouldn't have to carry all those supplies with us. So we could use the available thrust and propulsion to get there quicker. If you're familiar with the International Space Station, about a year ago they installed one of these inflatable rooms. Now they're not using it right now. It's only opened occasionally to go in there and take samples of the air and check for integrity. But Bigelow Aerospace has a vision of these inflatable structures on the moon, on the Mars, in orbit, to provide hotels for tourists, to provide outposts for settlers. So it's a concept that's being worked on. As I said, it's almost been a year since the one at the International Space Station has been installed. I'm not sure how much longer they're going to keep it there, but so far it's proved to be a fairly durable structure. Now, artificial gravity has been attempted. Of course, every time, if you've ever been to Epcot at Disney World and went on the Mission Space ride, you were actually on a centrifuge. They spin you around, and the rotation gives you a sense of increased force, like gravity, on the human body. Back during the Gemini program, Gemini 12, the astronauts attached a tether to that Agena rocket there on the right, and they tried to rotate the two objects around a common center to produce gravity. They were mildly successful. They had some issues trying to keep the tether taut, but it was an attempt to see if they could to generate artificial gravity. It's a little more complex than, say, going to your local carnival and they spin you up and then they drop the floor and you're stuck to the wall. The smaller the spacecraft, the faster it has to rotate, which becomes very disorienting to the human body. In fact, it almost killed Neil Armstrong. Gemini 8, Neil Armstrong and David Scott were conducting experiments, and the thruster system on their Gemini spacecraft malfunctioned and started firing. And it spun them up to, they were rotating one rotation every second. And it was getting so fast that the astronauts were on the verge of blacking out until Armstrong was able to cut the power to that particular system. And then he had to use the retro rockets that they would normally use for landing to counteract the spin. As a result, they came back early and they way off course, but they did survive, which was one of those little unknown events in our space program that be an interesting topic at some point. But NASA was under a lot of pressure at that point. They had just lost 2 astronauts when their jet crashed in St. Louis in bad weather. So to lose 2 more in orbit would have given people pause on the space program at that point. One of the topics that I've found doing a lot of research for this talk tonight is a temporary deployable magnetic field using a superconducting wire, deploying it from the spacecraft and using that to charge it and deflect incoming high energy particles from the galaxy. So I don't think they've worked out all the details, and I haven't seen anywhere where they've actually tried to deploy something like this, but it's something that people have studied. It's a possibility of one approach to trying to protect the spacecraft and the astronauts in it, because shielding alone will not protect the inhabitants. Now, NASA has these forums where they bring in folks, and these folks try to look out 30, 40 years and come up with objectives that seem really far-fetched today, but something that could be worked on and maybe reality in the future. And this year, Dr. Jim Green, who is the director of NASA's Planetary Science Division, gave an interesting talk at the workshop, and he proposed putting up a magnetic shield in front of Mars that would deflect the solar wind, because if you would follow the MAVEN mission that's out at Mars, it's pretty much concluded that the solar wind is responsible for ripping away most of Mars's atmosphere. So this particular proposal would try to protect Mars from the solar wind and allow the atmosphere to recover. And if the atmosphere recovers sufficiently enough, it would provide protection to future colonists on Mars. So again, it's one of those wild dreams, one of those science fiction concepts, but you know, there's science behind it, so it's not totally impossible. It's just something that we would have to develop the technology to invoke. Now, the other interesting research I came across was putting people under No, it's certainly something that you see in a lot of science fiction movies, uh, where you get to sleep most of the trip away. In fact, there was a movie just out last year called Passengers in the theaters. If you have people um, in some kind of induced coma, of course, they don't need as much oxygen or food or resources. Time passes quickly. And there's actually some medical experience on this where people have been put into a therapeutic hypothermia for up to 2 weeks in medical emergencies. Now, I don't believe there's any work been done on healthy people, but certainly this is something that the medical community uses. And what they do is they cool the body. And one of the ways they do that is they inject a cooling mist through the nostrils that cools the base of the brain. And it brings the body temperature down to about 93 degrees, where you go into a semi-coma. And they might put a mild sedative in there too, just so that you wouldn't have the shivering response. But you would get all your nutrients through an IV. They could stimulate your muscles with electrical pulses, and you might actually arrive on Mars in better shape than when you left. And you could actually use a high rotation rate of the spacecraft, because the passengers would not be aware of the disorientation. So it's something to think about. There's an interesting paper that's out there on the internet that goes into all the medical techniques that could be used and could be furthered. So it's an interesting way to pass the time if you're going to spend 9 months in space going from Earth to Mars. I had one more slide to finish it up. Just a piece of advice. Try not to breathe vacuum, because you can't. If you happen to go out of the space station or your space capsule, you have about 15 seconds before the lack of oxygen, you'll become unconscious. Now you can survive for a couple of minutes if someone brings you back in and revives you. They did some studies early on. In fact, there was one gentleman who was in a vacuum chamber back in the 60s doing some work and got a tear in his spacesuit. And he did black out. The last thing he remembered was the water on his tongue starting to boil away. But they pulled him out, and he had been exposed for over a minute, and they were able to revive him with no apparent damage. I think they've done animal studies, and chimpanzees have been able to survive in a vacuum for almost 2 minutes. So you can survive, but after 15 seconds, you're going to need someone else to come and get you. So that wraps up my talk for tonight. I appreciate you coming out on a miserable, rainy evening. If you have any questions, I'd be glad to try to field them. Yes? I'm sorry?
The summer program? You mind if I make
Oh, no, go right ahead.
Okay, yeah. So, alright, this summer, in July, we're offering a summer program for kids 5th through 8th grade. I don't know if anyone here is 5th through 8th grade, but, parents can come and hang out in the back too. It's a 6-day program on the history of astronomy. I'm doing it. And there's an activity every day. It's 7 to 8:30, and then the 6th day, which is a Saturday night, is when parents can come and see all the things their kids have made during that week, and we observe together things that the kids will be studying. So if you yourself are a 5th or 8th grader, or you know any 5th or 8th graders, I've got some brochures over there if you want to come grab one afterwards. So.
Thank you, Lise.
Thank you.
Anything else?
Yeah, Bill, on those microbes,
Yep.
do they grow any different in space? I mean, do they notice anything weird about them?
Yes. The microbes, Don's question is whether the microbes change or mutate, and they do seem to. They have different properties. We haven't seen any large alien creatures with multiple limbs, but the microbes are affected by both the weightlessness and the local radiation fields. Yes, Steve.
When you were talking about the radiation problem, is it possible they could use water as a shielding medium on the wall of the station? I mean, isn't water...
Yes. Now, the question is, can you use water as a shielding medium? Water is a highly effective shield in that it slows down the galactic radiation. So you don't have that. If you use dense materials, the galactic radiation will either pass through them or it will interact with the shield and scatter. Water will tend to slow them down, so they can be stopped by a more dense shield later on. Now, you certainly could configure a spacecraft where your fuel tanks were around the crew compartment, so that you had a liquid shield. Right, because every pound of payload you carry is an expensive endeavor. You'd want to minimize just carrying excess payload. But if you could somehow use the fuel as both fuel and shielding, it would be effective on the galactic radiation. Yes.
You said you were going to, there's a theory that you can shield Mars from the solar wind.
Yes.
How big would that have to be in order to protect Mars?
I don't know if they went into the design too much. It was more of the physics. They would park it out at one of the Lagrange points, one of the stable points in between Mars and the Sun. So it'd probably be 1 million miles out or so from Mars. So you would get that advantage of being able to produce a fairly large shielding effect with a fairly small object. But still, it's going to take a lot of power, and I imagine it's going to have to be of somewhat sufficient size to produce the deflection of those charged particles that is necessary. You're talking mostly protons, high energy protons that are being emitted by the sun as far as the solar wind. But I haven't seen any estimates of how physically large that shield would have to be. Yes?
Along the same vein, should the Earth get bombarded and we don't have our shield, it would strip away everything that's saving us now.
That's true.
Mars got stripped clean. If that happened to the Earth's atmosphere, we could end up as dusty as the Mars.
Yes. If for some reason our magnetic field weakened, and it's entirely possible that it could happen. It's happened on the moon. Mars had a magnetic field at one time. The magnetic field tends to be generated by a dynamo inside where you have a liquid core that's rotating. Mars, the moon is also, its core has cooled to that point where it no longer generates a magnetic field. So yes, if that magnetic field starts to fail, you will see more erosion of the atmosphere. You will see more penetration of radiation into the lower altitudes. So just like when we damaged the ozone layer, we were allowing more ultraviolet radiation into the lower atmosphere, and it was doing measurable harm to living species.
Thank you.
Well, thank you very much.